Alright, so solving this equation using possible rational zeros as a second approach, we are given on this problem, what were we given? One of the roots, right? There's a complex root. We were given negative 1 plus I root 3. So if the objective is to find all the roots or solutions, given one of the roots, because this is complex, we know the conjugate also is a root. We got this degree 3 polynomial equation, meaning there's 3 roots to find. We've got 2 of them so far. Now, using possible rational zeros to assist in finding the remaining ones, to review how that works, that's when we list our P's and our Q's, right? The P's represent all the factors of the constant, so all the factors of 16. Factors of 16 would be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, and plus or minus 16. We are taking all the factors of that constant, we are dividing by the factors of the lead coefficient, which in this case is 1. So we're just dividing by plus or minus 1. Meaning we get that top row back when we do that division. And we've narrowed down our search to these possible roots that could work as solutions to this equation. So from this sampling, the idea is we pick a number, we put it in the box for synthetic division, we spell out our coefficients on the polynomial, which is 1, negative 2, negative 4, negative 16. After plugging that number in the box, the goal is to get a remainder back over here as 0. Now, we can spend some time choosing some numbers to see what works. We also appreciate that if we graph this function and look to see where it crosses the x-axis, that can save us some time, because one of these values should represent an x-intercept. But we've already solved this once, and we know what the solution is going to be, right? We know it's supposed to be 4. So if I graph this, I should see that it crosses the x-axis at 4. With that understanding, 4 goes in the box. I show my mathematics here to justify that this is a root. So bring down the 1, do the synthetic division, multiply back the box here, get 4, add through, get 2, multiply back the box, get 8, add through, get 4, multiply back the box, get 16, add through, get 0. That justifies that 4 is going to be a solution here. So x equals 4. X equals 4, and then of course we've got our 2 other roots up here, negative 1 and plus or minus I root 3. As far as mathematics is concerned, to justify your solutions here, this would justify your solutions enough, all the work you see up here. Now, for good measure, I do want to show you something. I want to show you that by finding 4 as a root here, we basically have taken the factor of x minus 4 and divided in to give us this resulting quadratic, where we understand if we set that equal to 0, that would give us the other 2 roots beyond this 4 we've already found. That's not factorable, so if we use the quadratic formula, x would equal negative b, so negative 2, plus or minus square root of 2 squared 4 minus 4 times a, which is 1, times c, which is 4, all over 2 times a. So just 2. Cleaning up the discriminant, you've got negative 2 plus or minus, this would be what? 4 minus 16, so negative 12. If I take the square root of negative 12, square root of the negative means the I pops out. Square root of 12, that breaks down, right? It's 4 times 3. So we take out a 2, it'd be 2I root 3, all over 2. We look for that magic combination of factors here that are shared between these three values. Of course, 2 is shared. If you take 2 and divide into each of those, obviously it leads us right back up here to -1 plus or minus I√3. And finally, for equally good measure here, the factorization. The factorization of this polynomial that was given as an equation would be x minus 4, since 4 was a root, times x minus the -1 plus I√3, since that was given as a root. And then the final factor would be x minus the -1 minus I√3, because that was the conjugate of the given root. Degree 3 polynomial, there's 3 factors. But let's see, long story short on this one, we're factoring this polynomial. Okay, that's what the directions are basically asking us to do here. So no roots are given. Since no roots are given, one way to go about our business here is to list some possibilities. If we're going to list some possibilities, now we've done this a few times, kind of cut to the chase. We know we're taking the factors of the constant, we're dividing by the factors of the lead coefficient. So since I'm dividing by 1 here, I'm just going to get the factors of the constant back, right? So factors of 20 would be 1, 2, 4, 5, 10, and 20. So I narrow down the possibilities. From these possibilities, I choose those values at random, stick them in the box, spell out the coefficients on the polynomial. As always, make sure that every coefficient is accounted for. If you have to put some zeros in some places, put some zeros in some places. But our objective is to get a 0 back in this box. So what numbers should we choose from up here? To save us some time, we go to the graph. We graph that polynomial. So since we know some possibilities here, it should make sense that where this crosses the x-axis is at least one of those possibilities. Looks like it crosses at -5, right? Also seems to bounce off of a -2. We haven't really talked about what it means when it bounces. I'm going to show you what that means here in a minute. But let's take the -5. We know that's one of the possibilities. Let's throw that in the box. -5 is serving as a root. When I go through the synthetic division here, I should get a remainder back as 0. So going through that, let's see how this works out. Looks like it works out just fine. Since we're asked to factor this, I could go ahead as I find roots and start listing some factors. Since -5 is a root, x plus 5 is a factor. I know I've taken x plus 5, I've divided that in to get this remaining quadratic of x squared plus 4x plus 4. At which point, usually we're setting this equal to 0, we're solving for x to get remaining roots, right? Now sometimes we're going to have to do that, especially if our roots are irrational or we get some imaginary stuff back, they're complex. But since we're able to factor this one factors to x plus 2, right? Technically, since we're asked to factor this polynomial, we can stop at that point because we know our remaining 2 factors. We've got x plus 2 and x plus 2, so we could say x plus 2 is a quantity squared up here. Now, as a side note, knowing if we solve these, x would be -2. Since you have 2 of the same factors, this -2 represents what we call a double root. And whenever we have these double roots, that's when you see on the graph that kind of bouncing effect off of that value. Right, graph just kind of comes down, bounces off -2, and then shoots back up. So if you ever see that on the graph, you know that you're going to get that solution basically twice.